In this module, we shall turn our attention to a special class of models based on tree models, namely the QBIS model. Recall that in the previous class or module, we learned about trees and how we can apply decision trees to classification tasks in machine learning. So before we get on the full ride to understanding QBIS models, we'll take a quick moment to refresh on the scenario that we discussed in the last class, where we used a decision tree to build a predictive model. Let us see. The scenario we talked about relates to the Google App Store. Now, let us recall that we talked about the possibility that you have a first job at a Google App Store. One of your job descriptions is to make recommendations to customers on apps in the store that they might want to first explore and download. Well, to begin to make recommendations, you like to make data-driven recommendations. So towards that end, you have collected data on 6 past customers to the store. Here is the data. The goal is to be able to predict what app a customer visiting the App Store would prefer. Is it Pokemon Go, WhatsApp, or Snapchat? In the past, the first row corresponds to the first customer who came into the store. This person is a 15-year-old female who eventually downloaded Pokemon Go. The second row corresponds to the profile of a 25-year-old female who eventually downloaded WhatsApp. And the third row is a 32-year-old male who eventually downloaded Snapchat. The big question before us is, in order to make a data-driven decision or recommendation of what app a customer should download, should we use gender or age, or should we use both? Or, if we may, which of these variables, gender or age, has the greatest amount of information in making decisive decisions about what app to recommend to a customer who comes into the store at a future date? To answer that question, let us consider this together. Take, for instance, if we were to make recommendations based on gender, we might have the following split. For females, FFF, you observe that there is a greater tendency to download WhatsApp as compared to Snapchat. Whereas for males, there's a greater inclination to download Pokemon as opposed to Snapchat. Well, that is if we decide to make a split based on gender. That is not the only variable we have information or data on. We also have age. So let's consider that. So if we decide to make our recommendation based on age, just age alone, and we decide to make a split for customers who are younger than 20 years old, so 15 years, 12, and 14, it appears we have a more decisive hit here. In other words, age seems to be providing more information in making a decisive recommendation to our future customers. For those who are under 20, based on past experience or past data, which we call training data, we would recommend Pokemon Go. And for those who are older than 20 years old, depending on whether they are female or male, we would recommend either WhatsApp or Snapchat. So what are the insights that we can see here? We represented the insights in this data set by a decision tree, in which case, if a customer at a future date is younger than 20 years old, our past data tells us to recommend Pokemon Go. Otherwise, if the customer is older than 20 years old, then depending on gender, whether female or male, will recommend WhatsApp or Snapchat. Take note that the most important variable in predicting the app, which is age in this case, was the one variable that was represented at the root node. In other words, the split was made based on age because it appears to provide the most useful information in recommending what app a future customer might want. So with this said, we're ready to communicate our insights. It turns out age is more informative in making decisive recommendations. And to that effect, at a future date, if a 34-year-old lady comes into the App Store, we can make the data-driven decision to recommend WhatsApp. And in that way, we can minimize uncertainties associated with the decision of what app to recommend to a customer. Now, having refreshed on the basic concepts of recursive partitioning that was used in decision trees for a classification task, in this module, we would like to build on that and review the use of regression trees, that is, tree models, for a regression or numeric prediction task. And we'll see if we can use QBIS models to improve on the performance of the regression tree model. So, to motivate our discussion in this module about regression trees and the QBIS model, we consider a business use case. In order for health insurance companies to make money, it would only naturally make sense that they must collect more money in yearly premiums than they spend on medical care of their beneficiaries. So that means that insurance would usually spend a great deal of time and effort and resources in order to develop models that can adequately help them to accurately predict the medical expenses of beneficiaries on their medical plan. Now, the reality is medical expenses are difficult to estimate because sometimes the most costly conditions are associated with rare health conditions. Still, more conditions can also be found to be more prevalent for certain segments of the human population. So, our goal in this analysis is to use collected patient data in order to make predictions of the average medical care expenses for different population segments. The usefulness of the insights that we'll be able to get in this exercise would be very useful in creating actuarial tables, which are used to set the yearly premiums of beneficiaries on a medical plan, whether higher or lower relative to the anticipated treatment cost during the year. So, without any further ado, let us look at the data collection process and what the data collected involves. So, the data includes 1,338 instances or patient data that are currently enrolled in the insurance plan. And the features or the variables on which measurements are collected has to do with the total medical expenses of the patient charged to the plan for the calendar year. In other words, the target or response feature or variable that we would like to predict in this case are the medical expenses of each of the 1,338 medical patients, and we hope to collect information or data from predictor features of each of these medical patients in the form of their age, sex, BMI, number of children, whether they are smokers or not, and the region of the United States in which they are located or resident. The data analytic tool of choice that we have been using in this class is R, so it's the same one we are going to be using in this module. So using R, we are able to carry on a data exploration of the data set, and using the scheme function, we have the following data summary. So number of rows, 1,338. There are 7 variables in this data set. 3 of them are factor variables or categorical variables, whereas 4 are numeric. So which 3 are categorical? You have sex, smoker, or region. And from our initial exploration, we can see that no data points are missing. Yay, that's a great one. And so we also have the complete rate, and for the factored variables or for the categorical variables, none of them are ordered. In this case, you have sex. There are 2 levels, in which case you have male and female, 2 different values. They're about evenly distributed. And for the numeric variables, we have age, BMI, children, and expenses, where expenses is the target feature. It is our hope that the information or data collected on all the remaining 6 variables from sex up until children will provide useful signals in predicting the medical expenses for the calendar year for each of these patients. And this model can be used to make forecasts in the future. Now, one well-known reality is that every data set that we use in building any form of predictive model has some amount of internal chaos in it. More or less a mix of signals and the noise. It is our hope that the way we'll be able to tune the predictive model will be very useful, will be very effective in separating the signals away from the noise and helping us to optimize the signals in the information, in the data set, in such a way that it can help us to sharpen our predictive performance. With that said, that means that we turn to a very important requirement before we build predictive models, and that is feature or variable selection. Well, since we want to build a regression tree and a QBIS model, we might ask, what are the requirements for selecting variables? The long or the short answer to that question would be that there is no unique way to pick variables that are best for a particular model. But the good news, to top it all, is that for tree models, they do have their own internal variable selection mechanism. And so we're going to depend on that. So, with that said, we reckon with the details of Max Kuhn and John Sin K in 2013 in the book Applied Predictive Modeling, which has the following good things to say about tree-based and rule-based models. The first being that they generate a set of conditions that are highly interpretable. In particular, for this module, what is most important to us is that these models can effectively handle missing data and implicitly conduct feature selection. However, they also suffer from 2 well-known weaknesses. 1, model instability. In other words, slight changes in the training data can definitely drastically change the structure of the trees and the interpretation that it lends itself to. And sometimes, most times than not, tree models can lend or can give us less than optimal predictive performance. With that said, let us move on to building the single regression tree. So like we did in the last class, we are going to call on the RPart library, and we specify the target feature that depends on every other variable in the training data set. In this case, our data splitting process is 70% for training data set and 30% for the test of validation partition. So what are the results we get from fitting the single regression tree model to this data set? Here it is. So we see that this regression tree is indicating that at the root node, it uses the smoker status in order to make a split on the root node, which means smoker provides the highest amount of information or information gain in predicting the medical expenses. And so for this path, we get to this point where we have the smoker, and if this person is not a smoker and is aged under 45 years old, there are 431 of them in the training data set, and the predicted medical expense is $5,559.09 for the year. So we have other parts too, and it's no surprise that those who smoke tend to have a higher medical projected expense for the year. So with that said, let's see how we evaluate the model on the test of validation instances. So here on the screen, I have the actual medical expenses on the test data set. And then we have the predicted values. We do recall from the last class that we do not want to test our predictive model on the training instances because that can give an overly optimistic impression of the performance of the model. So these are the errors. We'll see that for some instances, the error of prediction is low, and for some, it is incredibly high. And to look at the performance metrics, we have the root mean square error, the R square, and the mean absolute error of 3,505 on average associated with the single regression tree model. So at this point, we might ask, can we do better? And that is where the QBIS model comes to play. Remember the no free lunch theorem, that no particular predictive model is a one-size-fits-all, where it fits to every data. So we look to the QBIS model to see if it can improve in performance in fitting to this model. What makes the QBIS model different from the regression tree is that at the leaf nodes, rather than using the average medical expenses of all instances in that leaf node to predict the medical expenses for the year, it uses all those instances in the leaf node to generate a regression model, and this often results in more accurate results than regression trees. So with that said, we build a QBIS model, and here is a part output of the QBIS model. So for this part, for 227 cases that make it into a particular leaf node, and they satisfy this condition, if their age is less than or equal to 30, smoker is no, the outcome or regression model is medical expenses is given by this regression or estimated regression line. So at this point, we would like to evaluate the QBIS model on the test of validation instances, in which case you observe that the mean absolute error has reduced from what it was before. Formerly, for the single regression tree, it was about 3,505. And in this case, it has come down to $2,046.10 approximately. So with that said, we note that the QBIS tree model appears to be a better fit to this data. And in interpreting the results of the QBIS tree, we note that we interpret the regression line just as much as we would interpret the estimates of the regression parameters for any linear model, for any linear regression model precisely. And with that said, we look at the summary of what we have covered here. We've studied two methods of applied predictive modeling just to compare, and that was the single regression tree, which uses recursive partitioning to fit rectangular light boundaries to data. And we consider the QBIS model, which uses a hybrid of linear regression models and single regression trees. And what we found out is that the QBIS model outperformed the single regression tree model.